Sometimes the math becomes so much easier when we rewrite the problem in a certain way. Here's what I mean. Let's take a look at this infinite series and let's try to see if it's going to converge or diverge using the usual convergence test. Now we can see that if we try to apply the divergence test or the nth term test, it's not going to work since the limit will be 0. And we probably don't want to integrate that function 1 over 2 to the ln n or ln x. So the integral test is probably out of the picture. And we probably don't want to use the ratio or root test yet, because let's first try to use the direct comparison test. Let's try to find a comparison series to compare with our series. But what series should we compare our series to? That is the question. Could we compare it to the geometric series of 1 over 2 to the n, which is convergent? Well, that's not going to work because ln n is going to be less than n for all positive real numbers. And that would imply that actually 1 over 2 to the ln n would be larger than 1 over 2 to the n. And 1 over 2 to the n, as we know, is a geometric series that converges. And if your series of terms is larger than a convergent series, that is no good. So what other potential series could we compare our series to? Well, that ln is a hint. So when I give this problem to my students, I often try to point their attention to that ln, because it turns out the series we should be comparing our series to would be this, 1 over e to the ln n. E, as we know, is the natural number. It's about 2.718, which means it's larger than 2. So that would imply that the inequality should be in this direction now. 1 over 2 to the ln n is actually greater than or equal to 1 over e to the ln n, which simplifies to 1 over n, which is the infamous harmonic series, which is well known to be divergent. And now we're in business because our series, 1 over 2 to the ln n, is larger than or equal to 1 over n for n greater than or equal to 1. And that is the direction of the inequality that we need. If your series of terms is larger than or equal to a divergent series of terms, then by the direct comparison test, your series will also be divergent. So now we have shown that our series is a divergent one. Easy peasy. And that's the beauty of math sometimes. With the proper insight, the math just maths itself. In any case, I hope you're doing well. Make sure to hit that follow button for more math content. And as always, I'll catch you on the next one. Take care.